recording. So for number 7, it says at noon, ship A is 30 miles south of ship B. So here is ship B, and here is ship A. And we know that this initial distance between them is 30 miles. Okay. And it says that ship A is sailing north. So I'm just going to sort of draw that it's moving north at a rate. So we're going to say A is going north at 15 miles an hour. And then it also says that ship B is sailing west at 10 miles an hour. Say west, 10 miles an hour. And we want to find the time when the distance between them is at a minimum. So B is going from here to somewhere over here, and A is going up and getting closer to this value of B. And so we want to know when along here, and let me get a different color here. I'm going to draw a right triangle, maybe. There we go. We're going to have a right triangle here. And so we're looking for when is D at a minimum. And so what we need to do is we need to figure out values in the same variable for the length of the segment between A and B, and then the length of how far B has gone. And so if we do that in terms of time, let's call T equal the number of hours. Then this distance from here to here, if it's moving at 10 miles an hour, would just be 10 times the number of hours. So that one should be 10t. And this one started at 30, but it's getting smaller by 15 every time period. So this one, this distance ought to be, let's get rid of this. Well, we'll just call this 30 minus 15. That sound good to everybody? Sophia, I know you were the one asking about this. That makes sense how we got the setup for those two, 10t and 30 minus 15t?
Yeah, it does.
Okay, cool. And so then now it's just the Pythagorean theorem. So we'll say d squared is equal to 10t squared, or 100t squared, plus 30 minus 15t squared. And then I'm going to stop there. I'll let you guys do the rest of the calculus work on it on your own. But that's the setup for that one. Everybody okay with that?
Yes.
Cool. Yeah.
So why are we doing the 30 minus 15d?
Well, because we're looking at the length of this, the length of the line between where A started and where B started. And so we know it started at 30 miles, but as time passes, it's decreasing by 15t. It's decreasing by 15 miles every time period.
Okay, so it's about the distance A is from B's original point.
Right, because as it wants to know when this distance is at a minimum. Well, as this one sails this way, this one's sailing. So this is getting, this vertical distance is getting smaller, whereas the horizontal distance is getting larger. So we gotta take both of those into account at the same time.
Okay, got it. Thank you.
All right. So we'll have a little more time towards the end today, I think, where you guys will be able to work a little bit. And if you have any questions, you can ask me questions on some of the other ones. But let's move into the last little topic that we're going to do, which is related rates. So related rate problems are basically just problems in which you are looking at how one variable changes with respect to time in comparison to a bunch of other variables within the problem. So once again, the most important thing you're going to have to do here is figure out what it's asking, read the question until you really understand what's going on. And then from the wording of the problem, you should be able to figure out which variable you're looking for the rate of change of and which variables you know the rate of change of. And we'll just sort of make a list of all the things that we know how they're changing and want to know how they're changing off to the side. And then just like in the optimization problems, you're going to want to draw a picture. The pictures will make this much easier. But there's a little bit of a caveat to that. When you draw your picture and start labeling it for related rate problems, only label constant things at the beginning. Okay? Don't label things that are changing. So if I go in and I say something like, for example, in this, if this had been a related rate problem, this distance started at 30 miles and it's getting smaller. Since that's changing, we don't want to label it as 30 miles if this was a related rate problem. So if something is changing, don't label it with a number, right? Even if it says, it starts at 27 miles and is decreasing, or if it says something similar to that, don't label it with a number. We'll have to put a variable into anything that's changing. And that's very important because that screws people up. All right. Then you're going to write an equation and you're going to differentiate both sides of your equation with respect to time. And the reason we're doing it with respect to time is we're looking at how something is changing at an instant in time. And so when we take the derivative with respect to time, it freezes it at that spot and looks for the instantaneous rate of change, because that's what a derivative is, right? It's an instantaneous rate of change. So the derivative with respect to time tells us the instantaneous rate of change of some thing with respect to time. And then at the end, we just plug stuff in and make sure it makes sense and don't forget our units. But I think hopefully as we start to do a problem and we'll look at the steps as we go, it'll make a little more sense. But this, very important. Don't label things that are changing at the beginning. All right. So we're going to give a shot at this one. So we're going to have a hot air balloon that is rising straight up from a level field. All right. Here's my level field. Pretend that's level. Here is my hot, I want it to be a different color. Here's my hot air balloon. Okay. And it is rising straight up from this level field. And we are over here, somewhere over here, tracking it from a distance of 500 feet from where it lifted off. And we are looking at how the angle of elevation is changing. So what's an angle of elevation? It's the angle between where you're tracking something and where that thing is. So that's this angle right here. And so we're looking at when that angle of elevation is pi/4 radians, we know that the angle is increasing at 0.14 radians per minute. We want to know how fast is the balloon rising at that moment. Everybody okay with my little picture that I've drawn based on what it's saying here?
Yes.
Okay, so let's try to label some things. First off, what can we only label in a related rate problem at the beginning? We can only label a
Constant.
We can only label a constant. So do we have any constants in here?
500 feet is a horizontal value.
All right, this is not changing, right? 500 feet from where we are standing to where the balloon took off from, not to where the balloon is, because that distance is changing. But from the takeoff point to our point is 500. That's not changing. And I already labeled this right angle. It says it's rising straight up. That right angle is not changing. Anything else that's not changing? Let's think about this. Is the distance here changing?
Yes.
Okay, let's call that, what do you want to call that? H or Y or something like that? A height?
Y.
Y? Okay, so distance in a Y direction. Okay. What about this angle over here? Is this angle changing? Is the balloon rising? Yeah, so even though we talk about a specific instant that we're interested in, at the moment that it's pi/4 radians, this angle is still changing, so we will not label this as pi/4. We will just label it as theta. Okay. Pretty good with that?
Wait, does a given angle even matter at all in this case?
Yes, it will once we get through partway through the problem, yeah. All right. So then let's think about what we know about the changing thing. So we know that the angle is increasing, right? It says that. The angle is increasing at a rate of 0.14 radians per minute. So that would be how the angle changes with respect to minutes is a measurement of time. So that angle is changing at 0.14 radians per minute. So we're going to call 0.14 our change in theta, d theta, dt with respect to time. So the instantaneous rate of change of that angle at the moment that we're interested in is 0.14 radians per minute. Everybody good with that or no?
Yes.
Okay. We want to know how fast the balloon is rising. What is that a change in?
Why?
With respect to what?
With respect to time.
With respect to time. So dy dt is what we are looking for. We want to know how fast is that balloon rising. We want to find dy dt. The only other distance that we have in here is the distance from here to here. Are we given any information about that whatsoever from the point where we're at to where the balloon itself is actually at? Are we given a distance at any point? Are we giving a rate at which it's changing?
No.
No. So chances are we won't need to use that in the problem. Now, sometimes you might need to relate some of the other variables in there to find these extra distances. But in this case, we're not going to. So we're going to just ignore that and see if we can write an equation that relates theta and y, perhaps also using this constant. So anybody have an equation that you think will work for that? Can be any sort of equation that relates theta and y.
Cosine.
What's that?
Oh wait, no, sine.
All right, so sorry, what's the equation that we're going to use to try to relate y and theta together?
500 divided by sine theta equals y.
I don't think that that's true. 500 divided by sine theta is not going to equal y. Let's think of something that's a little bit simpler.
Tangent theta is 500.
Yeah. Say that again?
Tangent theta is y over 500.
Yeah, that's going to relate y to 500 pretty easily and include that theta, right? Tangent theta is y over 500, opposite over adjacent. Or we could rewrite this as 500 tangent theta equals y. Everybody good with that?
Yes.
Yeah.
So the simplest equation that relates them will generally be the best. And so now let's look at our steps. We've understood the problem. We know which variable whose rate of change you were looking for, and we know which variable whose rate of change we knew, right? We labeled those. We're looking for dy dt. We knew d theta dt. Okay. Then we drew a picture, labeled what was important. We only labeled our constant quantities at the beginning, and then we put in some variables for other things that were changing. It's okay to put in variables for things that were changing. Then we wrote an equation relating our variable to the variable we knew. So we got that. Next step, differentiate both sides of the equation with respect to t, right? So since we're differentiating something that has a theta with respect to t and a y with respect to t, each time we take those derivatives, we have to attach a d theta dt or a dy dt term to them. So we're going to differentiate with respect to t both of these things, which ought to give us 500 secant squared theta d theta dt is equal to just dy dt. Good or no?
So where did this d over dt come from?
So that's what we're just taking the derivative with respect to t of both sides of it. So the reason we're doing that is because we want, this equation just tells us, well, what is y when theta is whatever we plug into it, or what is theta if we plug in a certain value for y. But we want to know how is y changing with respect to time, not just what is the height of the balloon, but how fast is this height changing. So what is the rate of change of y with respect to time? What is it, feet per minute that this balloon is increasing?
Because we're taking the derivative of tangent theta, we put the theta above the dt, so it becomes d theta over dt.
Right, because we're taking the derivative of something with this variable, theta, with respect to t. Just like when we do something like x squared plus y squared equals xy, we take the derivative of both sides with respect to x, right? When we do that for our implicit differentiation, well, when we differentiate the x's, we just get 2x because we're doing it with respect to x. But when we do the y's, we get 2y dy dt. Sorry, dy dx, because we're differentiating with respect to x. Well, here we're differentiating with respect to t, but neither of these variables are t, so they have to get these d theta dt or dy dt terms attached to them.
Okay, thank you.
Does that make sense?
It does. Yes, it does.
Yeah. It's just implicit differentiation, except that we're not doing the derivative with respect to x, we're doing it with respect to t. And so since none of these have t, they both get that extra added piece in. Everybody good there or no?
And that just comes down to the chain rule, right?
That's exactly right. Yep.
Okay.
Cool. All right, so now we have 500 secant squared theta d theta dt. Well, do we know what theta is at the moment we're interested in?
Pi fourths.
Pi over 4, right? Yep. Pi fourths, pi over 4. And so all we have to do is plug in our theta value that we are interested in, or d theta dt at that exact moment, and that should give us our dy dt. So we should have 500 secant squared pi over 4 times 0.14 equals dy dt. And what does that give us? What's the secant of pi over 4?
The secant of pi over 4 would be 2 over root 2, and then squared would be 4 over 2.
Exactly. So that's a 2, 4 over 2, and 500 times 2 is 1,000 times 0.14 ought to be 140 feet per minute. Any questions on that? Everybody good with that?
Yeah.
Everyone good or no? Questions? Did my Zoom die again?
No, we're here.
Sure.
We're good.
Oh, okay. All right. Just making sure. Everyone's good. All right. Let's try another one. I'll give you guys a second to read through it and then we'll start working on it. All right, everybody got a chance to read it and have a general idea of what's going on?
Yep.
All right, so we've got a police car. Here it is. Very realistic looking. There's my police car. It's approaching a right-angled intersection from the north. So it's going this way and hitting this intersection. That is not a very straight line at all. And then it's chasing after a car that's turned the corner and is heading east. So at some point that car is over here. Okay. And we are given some information that when the police car is 0.6 of a mile north of the intersection, so this is going to be 0.6 of a mile, the speeding car is 0.8 of a mile to the east, and the distance between them is increasing at 20 miles an hour. The distance between them would be the hypotenuse here, right? And we know also that, let's see what we say, the distance between them is increasing at 20 miles an hour, and the police car is moving at 60 miles an hour. Everybody good there or no? Is this a picture you would have drawn, hopefully?
Yeah.
Great. All right. What in this problem is not changing?
The distances from the intersection.
This police car is not getting closer to this intersection?
It is.
It is. So this distance is changing, right? What do we want to call this then? Let's not label it with a number. Let's label it with a variable. It's in the y direction. How about y? Do we feel okay about calling this y?
Yes.
All right. What about this distance from the intersection to where the speeding car is? Is that distance changing as the car moves?
Yes.
Yeah. So let's call that, since it's in the x direction, x. What about the angle in between x and y? Is that changing?
It's right angle.
It's a right angle, right? It's a right angle intersection. That's not going to change. Okay. We also know that the distance between the two cars here and here is increasing. So this distance is changing. So let's call that something. What do you want to call that? We got x and y. How about
Z.
I guess I was going to say like q or something, but I guess x, y, z makes sense. And that's changing. Y is changing. X is changing. It's all changing. So we just got a bunch of variables. How can we relate those variables together? How can you relate the two legs and the hypotenuse of a right triangle?
Pythagorean theorem.
There we go. Okay. So x squared plus y squared equals z squared. And then let's talk about what x, y, and z and their rates of changes all are. So at the moment that we're interested in, what is y?
0.6.
0.6. What about the moment that we're interested in, what's x?
0.8.
0.8, okay. And how fast is the speeding car going? What is its rate of change with respect to time? That's dx dt. How does that change? It's going at what speed? We don't know, right? What is the speed of the car at that instant? So that's what we're looking for. What about the speed of the police car? What's dy dt? How is y changing?
60 miles per hour.
All right, it's 60 miles an hour now. Tell me about y. What's happening to y as the police car approaches this intersection?
Decreasing.
It is decreasing.
Decreasing. So should its rate of change be a positive value?
No.
No.
No. If it's decreasing, its rate of change should be a negative value. So we're going to call that a negative 60. And anytime the rate of change of something is negative, if something is rate of change is decreasing, or if the distance is decreasing, then you need to make sure that your rate of change is a negative value. And what about your dz dt? How is z changing?
$20 miles an hour.
And it says specifically that it is increasing at 20 miles an hour, so that'll be a positive 20. Good or no?
Good.
Cool. All right. In that case, let's see what we can do with this formula. What do we need to do with it? We've done everything. We've done this. We've understood the problem. We've drawn our picture and labeled it. We've written our equation. We have to now take the derivative of both sides with respect to time. So what's the derivative of x squared with respect to t?
Two x times dx dt.
Good. 2x dx dt. What about of y squared? That should be
2x dy dt, or 2x times 60, or 120x, or 120y.
Well, let's just take the derivative first. So 2y dy dt, right? We'll plug all the stuff in a second. And then the z squared ought to be what's the derivative of z squared?
2z dz dt.
2z dz dt. And now we will plug everything that we possibly can into this. So 2x dx dt ought to be 2 times 0.8 times dx dt, which is what we're looking for, plus 2y, so that'd be 2 times 0.6 times dy dt, which is negative 60, equals 2 times z times dz dt. Well, dz dt is 20, but we don't actually have z, do we? So how can we find z?
X squared plus y squared square root.
Right, just using our original x squared plus y squared equals z squared, right? So 0.8 squared plus 0.6 squared equals z squared. And what does that give us? Z equals
1.
1. So we'll over here say z is 1, which means we'll put in a 1 there. And so now all we have to do is solve this. Should be fairly simple. Solve this for dx dt. So we've got 1.6 dx dt equals, what do we end up here? This is 40 and this is what, 72. So 1.6 dx dt equals 112. And if you divide by 1.6, what does that come out to be? Looks like that's, I think, 70, yeah? Good or no? Any questions on that? Everybody good with that? Okay with that? Not okay with that?
Decent.
Decent. I mean, any questions or no?
No.
All right, let's try to do another one. I'll give you guys a second to read through that and figure out what we're doing, and then we'll get started with it. All right. So what do we have here? We've got a conical tank. We got a cone and the point is down. There's my cone with the point down. Everybody good there? Everybody got that from here? It's a cone with the point down. Okay. What do we know about this? Well, first off, we've got water rising up in it, right? It's filling up. So at some point there's some amount of water in it, right? Is there anything else we know, maybe specifically about the cone itself in general, that is not changing?
The height of 10 and the radius of 5.
All right. So the entire height here is 10. Okay. And the radius is 5. All right. And then we are interested in how fast the water level is rising when the actual water level is 6. So is this 6 changing or no?
Yeah.
Yeah, so I shouldn't label that as 6. Let's just label that as, what do you want to label that as? H or Y or?
H.
H, okay. So H is changing. Let's see. And then what is each, as this fills up, it's just making a cone. It's just like start with a really small cone and the cone gets bigger, like the cone of water itself, right? So this has a radius to it, but that radius changes as the cone fills up further, doesn't it?
Yes.
Yeah. All right. So we want to know how fast the water level is rising. So that'd be a change in H with respect to time. So we're looking for dH dt. And we are given this, how fast the water is flowing into the tank. And what is that a measure of?
Volume.
Yeah, it's a change in volume. So dV dt is 9. And we can be clued in, even if we weren't sure if that was dV dt, we could be clued into it just based on the units, right? They're feet cubed per minute. And so that's something changing with respect to time, and it's cubic feet, which is always going to be a volume if it's cubic feet. Good or no?
Good.
All right, cool. So how do we relate volume to height in a cone? Volume is
1/3 base times height.
1/3. Nope. This is a cone, right? Not 1/3. I mean, 1/2 base times height would be a triangle, but that's not the volume of a cone. What's the volume of a cone?
Pi r squared height.
Pi r squared height. Yeah, 1/3 pi r squared h. Okay, so that's good. That's up to a good start. But we are only interested in how the height is changing, and we have a radius in here, and we're not given a lot of information about the radius. We know that the instant that we're interested in, h is 6, right? We can write that off to the side, but that doesn't exactly tell us how that height is changing. So how are we going to get this all in terms of one variable, just like we had to do with the optimization problems?
D over D. D over basically just derivative. Take a derivative of both sides.
Well, before we do that, we need to get this all in terms of one variable, though. Because if I don't, I'm going to end up with a dr dt and a dh dt. And I'm looking for dH dt, and I'm given dV dt, but I'm not given a dr dt at all. So we want to try and write this all in terms of h. So is there a way we can relate h to r?
Is H just 2R?
Why would it be 2R?
Because it's a similar triangle to the 5 and 10 one.
Exactly. So this is a right angle. This is a right angle. So this right triangle and this right triangle at least share one angle in common. They also share this angle in common, right? So angle, right? This one is congruent and to this one, and this one is congruent to itself. And angle proves triangle similarity, which tells you that the ratio between the radius and the height of the big cone should be equal to the radius to the height of the smaller cone of water as it fills up. So we can say 5 to 10 is equal to R to H in our cone, or that R is equal to what? 1/2 H, right? And I think you said H is equal to 2R, which is good. But we need to replace the R in here because we got to do everything in terms of H. So I'm going to solve it for R equals 1/2 H. Good or no?
Good.
Yeah.
No. Wonderful. So volume is 1/3 pi R squared. So 1/2 H squared H. So volume should be 1/12 pi H cubed for this particular cone. Good or no? Good? No? Questions? Everyone all right?
Good.
All right. Now we can take our derivative with respect to t of both sides, which will tell us that dv dt is equal to 3/12 or 1/4 pi h squared dh dt. Right, and 1/12 pi is just a constant, so multiplied by, it's just a power rule there. Now we'll plug everything in. dv dt was 9. So we got 9 equals 1/4 pi times the h value that we're interested in, which is 6 squared, which is 36, dh dt. And we're looking for dh dt. If I multiply by 4, that's 36 over here, right? I'm going to divide by 36. That's just going to leave me with 1 equals pi dh dt, or dh dt equals 1 over pi. And it's increasing in feet per minute. Good or no? Questions there? Everyone good?
Good.
That's related rates. That's the basics of it. I mean, that's, they can be a little more complicated than this. They can be easier, like the ones we did at the beginning. But that's the whole idea of related rates. Anybody have any conceptual questions on related rates? All right, that's it.